All right, this is a look at two quantities in mechanical physics that are closely linked, which are impulse and momentum. First up is momentum. Momentum is basically a measure of how much motion an object has. Now that's a bit strange of a definition. So momentum can be thought of as how difficult it is to bring an object that's in motion to a complete stop. So if an object has a high momentum, we can say that it's hard to bring it to a stop. Or if an object has low momentum, that means that it's going to be fairly easy to bring it from motion to a complete stop. Momentum is a vector quantity. If a quantity is a vector in physics, that means it's going to have both a magnitude and a direction. For the direction of momentum, it's pretty simple. It's going to have the same direction as the direction of the velocity of the object. For the magnitude of the momentum, it's based on two different things, the mass of the object and the velocity at which it's moving at. So if an object has high velocity, it's going to be harder to stop. So we can say that objects with a high velocity have a high momentum. Also, an object that's heavier or has a higher mass is harder to stop. So objects with more mass have more momentum. So the formula for momentum is mass times velocity. And it looks like this, where the letter for momentum in physics is a lowercase p, which is a bit strange. It can't be lowercase m because that's already the letter for mass. So momentum p is mass m times velocity v. And then momentum doesn't really have any units for it. So if you are to give the units for momentum, it's just the units of mass, kilograms, times the unit of velocity, meters per second. I have a simple example here looking at two things in motion. One is a llama with a mass of 90 kilograms moving at 2 meters per second. The other is an alpaca, which is fluffier than a llama and has a mass of 60 kilograms and is moving at 3 meters per second. And I want to compare the inertia and momentum of each object. First, inertia is just based on mass. So the llama has more mass, so it would have more inertia. For momentum, I have to actually go through and calculate mv. So for the llama, I get 90 times 2. That's 180 kilograms meters per second. The alpaca is 60 times 3. And there I get 180 kilogram meters per second. So the momentums there are equal. As far as what those numbers mean, the llama has more mass, which gives it more inertia. So even though they're equally hard to stop, so if I want to bring them both to a complete stop, it would be the same amount of force required. But if I just want to change their velocity slightly while they're moving, it'd be harder to change the llama's velocity, but then it'd be equally as hard to stop each object. The other quantity here is impulse. Impulse is going to be equal to the change in momentum, and it's given as the product of force and time when a force is applied on an object. Just like momentum, there's no real special units for it. Units of force are newtons and time is second, so it has units of newton seconds. It also can have the same units of momentum, which is kilograms meters per second. All right, so there's something called the Implulse-Momentum theorem, which says that the impulse, capital J, equals the change is denoted by a little triangle, or a delta, it's a Greek letter, means change in, momentum, which is a lowercase p, and then impulse is force times time. And whenever you talk about change in physics, you're always going to do final minus initial. So I'm going to have the final momentum is mass times final velocity minus the initial momentum, mass, times initial velocity. And we're going to assume that the mass doesn't change here. And what I just wrote is not really a new formula. If I look at this, so I had force times time equals mvf minus mvi. If I factor out an m, I get mass times final velocity minus initial velocity. And then if I divide both sides by time, I get that force equals mass times change in velocity over time. And if I look here, I have change in velocity over change in time. The change in velocity over the change in time is going to be the acceleration. So what I have here is actually Newton's second law, which says that force equals mass times acceleration. So Newton's second law, force equals mass times acceleration, can be used to derive the impulse-momentum theorem. Okay, so here's another question, and this one deals with the impulse-momentum theorem, and it says that we have a car in motion, and then it's brought to rest after a collision, and to explain why an airbag helps protect the driver of a vehicle. So on top here, there's no airbag, and the driver is going to experience a significant force. On the bottom, there is an airbag, and what that's going to do is that's going to reduce the force. Now, in terms of why that is, I look at the impulse-momentum theorem. The momentum has to change. So this is a non-negotiable. There is a certain momentum the car has, and it has to go to zero. So the change in momentum is the same for the top case and the bottom case. Whether or not there's an airbag, there has to be a change in momentum. And that's equal to force times time. So I could either have one of two things be large in order to get the needed delta P, or change in momentum. If I have a large force, that means the time of the collision would have had to have been short. That's the case when there's no airbag. Now, if you add an airbag, what that airbag does is it takes the driver a while to go through the airbag, then the airbag gets pushed down, so that increases the time of the collision, which then decreases the force. So what an airbag does is it'll increase the time of the collision, which reduces the force on the driver. The next example, example C, deals with a ball being kicked. The soccer player kicking the ball applies a force of 30 newtons on a ball that has a mass of 1.5 kilograms. The time of contact in which the foot is touching the ball is 0.7 seconds. And the ball starts off at rest, so VI is 0. And I want to find the final velocity, or how fast the ball is after it's been kicked. So I'm going to use the impulse-momentum theorem here, which says that impulse equals change in momentum, where impulse is force times time. And then change in momentum is final momentum, so mass times final velocity, minus initial momentum, mvi. Here it starts off at rest, so vi is 0, which means there was no initial momentum. So the impulse, force times time, equals the gain in momentum, which is the final momentum. And then I want to find vf, so final velocity is force times time over mass. Now I just plug in numbers. I have 30 newtons times 0.7 seconds over 1.5 kilograms. So the final velocity here, the ball after it's kicked, is 14 meters per second. The last example question here has a ball hitting the floor. So it's going down at a given velocity. It rebounds out the floor and then starts going up with a different velocity. It's in contact with the floor for 0.02 seconds and has a mass of 0.5 kilograms. Now what's tricky here is that momentum is a vector and the ball does switch directions. So here I'm going to say that up is my positive direction. So I'm going to say it's going initially at a velocity of -5 because it's going downwards, and then rebounds upwards at 4 meters per second. So again, I'm going to use the impulse-momentum theorem, which says that force times time equals final momentum minus initial momentum. In here, I'm looking for the force. So I'll say that force is mass is constant. So it's mass times change in velocity over time. And now I just plug in my values. So the mass is 0.5 kilograms. The final velocity is positive 4 meters per second. The initial velocity was -5 meters per second. So I add the two speeds together. Over the time of the collision, which was 0.02 seconds, and I get that the force here is 225 newtons.